All right, welcome everyone. It's my pleasure to introduce Yao-Yi Chiang, who is a research associate professor in spatial sciences and the director of the Spatial Computing Laboratory at the Spatial Sciences Institute and the associate director of NSF's Integrated Media Systems Center at the University of Southern California. So today he will tell us about mining public data sets for modeling intra-city PM2.5 concentrations at a fine spatial resolution. Thank you.
Morning, everyone. I'm very happy to be here. This is 10 years ago. I was in this AI seminar when I first came back for PhD, and I was very happy to learn new stuff. So my goal today is to show you what we are doing at Spatial Sciences Institute, and hopefully you will learn something interesting. The topic I want to talk about today is about air quality. It's a very long title, but the idea is we want to be able to predict air quality at a really fine scale by using only public data set. And I will tell you why and how we do it. I'm Yao-Yi Chiang. I did my PhD in computer science at RSI. I'm now at USC campus. I teach data mining, so any student here wants to take my data mining, it's usually in the spring. So this presentation is based on a 6 spatial paper we published last year. There's a bunch of people on the author list. Jose Luis is paying for the project, so I was surprised that he's not here. Okay. So this is an NIH-sponsored project. So I will go through some basic introductions, tell you what's air quality, why this is important, what are the things that we are predicting, and I will show you our approach, show you some experiment results, talk about some ongoing work we're working on right now. Air pollution is a global problem if you haven't noticed yet. If you look at that map, it's what's on this map? Lots of colors, different countries, and showing PM2.5 concentrations. I will tell you what is PM2.5, but it's one type of air pollutant that you should be very careful about. But one thing, when you look at this map, there is spatial scale, it's country. So you look at air pollution at different countries, so it tells us the US and Canada seems to be okay, but is that the case? When you are looking at air quality, you don't really care about the country level. People usually generally care about where you live, where you work, and where you travel. So a fine spatial scale is important, but it's really difficult to calculate. So this is PM2.5 and PM10. If you're not familiar with this type of pollutant, these are small particles, and they're really, really small. So this shows you human hair, and this is the beach sand. PM10 is about this, and PM2.5 is even smaller than this. These are fine particles with diameters that are generally 2.5 micrometers and smaller. Once it gets into your body, there's no good way to get them out. So different countries have come up with a way to communicate with their citizens about air quality, and it's called Air Quality Index, AQI. So we are going to use AQI a lot in this talk, so I want to show you what is AQI. If you look at AQI, it's a bunch of color scales, so it's easier to communicate to the general public. If it is green, it's okay. If it is red, it means it's bad. At different level, you have different explanations. And the tricky part is every country has their own AQI scales. So these AQI scales is actually taking the measured PM2.5 concentration and convert it to a different scale. It's a piecewise linear function. And different country has their different piecewise linear function. Yes.
If you use a mask, like would it filter out for stuff? Are the masks also labeled by the PM size that they're filtering out?
PM2.5, you need to have very special mask.
I see.
And those are really difficult to read.
So the ones like the surgical type masks, they don't.
Surgical type mask doesn't work.
Will they work with PM10 or not?
PM10 probably doesn't work too, but there are other pollutant types that do. So it requires very special mask. But one thing I want to tell you about this chart is, I don't know about other countries. In Taiwan, sometimes we have really bad air pollution. So we have a lot of purple. And 1 year, the government just decided to change the function so that we have less purple. So color is important, but raw concentration is also important too. So this is the AQI, air quality index, that we are talking about. The challenges in predicting air quality is, there's a lot of challenges, but here I want to tell you, the first challenge is the monitoring stations are usually very sparse. Like in the US, EPA and sometimes local government has built all this monitoring station, like large equipment, and you have to have a piece of land to place this equipment. In Los Angeles, there's only 12 stations continuously monitoring PM2. So for locations that without a monitoring station, how do we predict air quality? So these are the 12 stations that I want to show you. If you look at, this is Los Angeles, if you are not familiar with map. This is Santa Monica, this is Marina del Rey, so there are 2 monitoring stations near the coast. This is further away near Ventura, there's one in the mountain, there's a couple ones here. So only 12 stations. The problem of 12 stations is you only have very few observations, and it's difficult to get predictions from these observations. But in geography, people talking about this popular first law of geography, which is all things are related, but nearby things are more related than distance. So based on that assumption, locations that are nearby should have a similar air quality, right? So can we use that idea to do spatial interpolation? Say, if I'm close to a monitoring station, I can interpolate my air quality from the nearby monitoring station. That's exactly how people do it right now. So if you go to the AirNow website, you will be able to see air quality prediction. But what's the problem of this map? It's air quality prediction, it has colors, but the spatial scale is very coarse, right? Because you only have 12 stations, there's no way you will be able to generate a nice interpolation of these predictions. And we took these 12 stations, we ran our spatial interpolation method. This is also very coarse. From this map, you will be able to see that, well, the only information you will be able to get is downtown is very bad. So these are at different time. Downtown is very bad, and some areas here are okay, but what if you are in Beverly Hills? Is it better than Santa Monica? We don't know. And there are companies that are generating models and for predicting its air quality, like Frizometer. Their slogan is there. This algorithm, this result is powered by proprietary algorithms, strict QA, and machine learning. So we trust them. But you look at the map, still there's not a lot of variations. Most of the regions have the same air quality. So how do scientists deal with this problem? There's a lot of work at USC on air quality modeling. I think since the 90s, Peck Medical School has lots of experts looking at the built environment, and how they react with air quality. So here is to show you that the bottom you see factories, construction sites, traffic, and open land. They all have some impact to the air quality. For example, construction site might produce fine particles and contribute to PM2.5 and 10 concentrations, but they have a schedule. So at different time, the impact is different. Traffic also have a different schedule, but also for different areas, the spatial distance of the impact is different. For example, in Los Angeles, do you want to live nearby a highway or not? Probably not. But when I say near, what do I mean? 200 meters, 300 meters, 500 meters? What is safe? We don't really know unless someone really go in and install smaller sensors, do a ground truthing, and identify how this air pollutant propagate through space. So traditionally, people are doing land use regression. That means they take variables that can describe the built area and run a regression model to identify air pollutant or AQIs at different locations. So this is from a survey paper. This is to show you how difficult this task is. That's a lot of text, but I will help you with. Every row here is a study, and every study here might cover a different country or a different city, different study area. So like the first one covers some cities in the UK and New York City in the US. The second one covers Canada. This one covers Portland, and one covers Taipei. The other one covers Beijing. So different locations. But why is different locations important? When you look at different locations, different dependent variables, these are the pollutant types they want to predict. Experts came up with different types of built-up environment variables for the prediction. For example, the first one used road traffic, urban land, elevation. The second one used traffic, land use, but it also used census. And some here use building density, population. Someone also even use address density. The Taiwan study used the location of ports, and the Beijing study used bus stops and restaurants. So the person who came up with this dependent variables, they did field study to identify important factors in that area. And once they identify these important factors, they then need to define a spatial distance. Remember, I was talking about how far away from a highway is important. For different area, it's different. The first one says it's 300 meters. The third one says it's 3,000 meters. So every location is different. I think UCLA and USC both did studies for Los Angeles regions for highway pollution, and they came up with different conclusions. So one example is PM2.5 concentrations is high, near 5 meters of highway in Los Angeles. This approach is very expensive. You need to have lots of PhDs, MDs working on these air quality models, and they do not scale well for predictions at various spatial and temporal resolutions. For example, if we build a model for Los Angeles, now we want to reuse the same method for San Francisco. Can we just do it? We can't. We need to go to San Francisco, we need to install some local sensors, and we need to do this all over again. And sometimes these methods relies heavily on data sets that are not easy to obtain, like traffic data. So how many of you have ever accessed real-time traffic data in a large scale, like 5 years traffic data? No, it's hard. It's expensive and difficult to get. So can we do better? Yes, that's what the talk is about. When we were working on this problem, we worked with people from the medical school, and they told us the problem, and for predicting air quality, they promised to send us a list of important variables in the spatial distance, but they never did. So we look at the data, we think we can use the data to help us do the prediction, and hence the approach here. So our approach is data-driven, and the problem that we want to solve is we want to predict air quality for locations that do not have a sensor. Right? So we have 12 sensors. We know the air quality for these 12 sensors. How about other sensors? Can we identify fine scale variations of the air quality? And the way we do this is we use public. This is probably too small on the screen, but we first use public data set to help us describe built-up environment for any locations in Los Angeles. Then we use known AQIs from the monitoring station to help us do the prediction. So if you look at the chart here, these are 5 locations, and 5 locations showing very different built environment. The first one here is a residential area, so mostly you have single-family houses. And the second one here is single-family houses, but you have some industrial land, and there is a highway nearby. The third one here is, this is Marina del Rey, I think. You have some single-family houses, and you have very close to the ocean. This one is near USC, so near a large university campus that is open, supposed to be good for airflow, but it also attracts a lot of traffic. I don't know where this one is, but it's near a park, so near open space. So if we, for all this location, assuming that we have a monitoring station and we know their air quality, for a new location that we know the built environment, can we predict their air quality? If we look at data, this is the PM2.5 AQI from one monitoring station covering a lot of months. So we have a couple years data, but this is to show you the time series data of PM2.5 monitor. And around this monitoring station, we have all kinds of man-made objects like highways, restaurants, factories, or single-family houses. So how do we use these surrounding features to help us make the prediction of the time series data? That is the goal. So before I talk about our approach, I want to spend some time on the data infrastructure. This is a project with Jose Luis here and Keck Medical School. They have a grant from NIH. The entire system is built on a scalable framework, and we are using the data stored in the system to do the prediction. So the system takes sensor data from UCLA. You have biometric data from kids wearing smart watch, and we have AirNow data, EPA AQMD data to tell us what's the current PM2.5 concentration at all these 12 monitoring sites, and some of our data from the traffic. The idea is, how do we use all this data to help predict asthma attack in small kids? All this sensor data first going to Kafka as the message queue component, then going to Spark Streaming, Spark, and store data on Postgres to handle spatial location data, spatial data, and have HDFS to store the information as well. And on top of that, we have a lot of different types of analytics tools so that data scientists can work on the data. We have support Spark R, Spark MLlib, and a Hue interface. So that's the entire framework that we store data and manipulate the data. So what is the data? The first data source that I want to show you is the air quality data. So here is a sample of the data. And we have 12 monitoring stations. This is a sample of 2 stations. So for every station, at every hour, it will send us back PM2.5 AQI monitored at that station. And this is Central LA. This is San Gabriel Mountain. The second data source that we use is OpenStreetMap data because we want to be able to generate a feature vector that can help us characterize the built environment of any locations in Los Angeles. So we take OpenStreetMap data. This is to show you the variety of the data types in OpenStreetMap. We have land use data. Land use data has lots of polygons. Land use data tells you if this is industrial land, if this is residential area or business area. And polygons are areas. So it will tell you how big is this area, where is the boundary of this area. We also have roads, lots of roads, and water area. It could be a creek, could be small pond, or other types of water areas. We have buildings, all kinds of buildings, airways. This is runways in airports. And all these different geographic features, they also have their subtypes. So if you're interested, you can take a look at OpenStreetMap wiki. It's very comprehensive. So one example is for buildings, we know that the location of the building, is it commercial building? Is it apartment, house, industrial, or school? So we have lots of information about the environment, and we have 12 yes.
Do you have information about like how much green area there is?
We didn't use it, but we could get those. Right, those will be like land cover. Right? So now we have this time series data from 12 monitored stations, and we have this data source to describe the environment. But we still don't know which variable in the built environment affect the PM2.5, and also from what distance. So what do the data tell us? The first step to discover this PM2.5 and environment patterns is we want to identify the monitoring stations that have similar temporal pattern of PM2.5 AQIs. So on the left side, that still shows you the 12 stations. On the right side is their grouping result. So this is the result we want. We'll say, hey, these two stations have similar temporal pattern of PM2.5. Say at 2 p.m. on Tuesdays, they are always high. On Monday, at 1 p.m., they're always low. Traditionally, if we just use distance, this two, the blue one and the yellow one, will be more similar than these two yellow ones, right? But we want to first cluster. Yes.
Sorry to interrupt. It strikes me that you're not talking about weather a great deal. You're talking about the airflow. You're talking about built environment, but you haven't really mentioned weather data. And given we're talking about wind and that type of question, is that something important that you have?
Yeah, weather is important. Our experiment shows that weather can help us to improve a little bit of the prediction accuracy. I will talk about that. Okay. So for this approach, we only use built environment. We did not consider weather.
The map on the left, are the stations randomly color-coded, or?
Yeah, they're randomly color-coded.
I have one question. What I saw the problem was the station is too big, so it's too expensive. But I assume there are some thing like a smoke detection that size we can put it out where we have more data, right?
Yeah.
That will reduce the problem size, or we have more data to like train to like test, right?
Yeah, I will talk about that too.
Oh yeah.
All right. So first step, we want to group of the similar temporal pattern. I want to show you what we mean by similar temporal patterns. And these are again the hourly AQI data. and the red lines and the blue lines shows you the pattern. And these 3 are from the total area. These 2 are in the San Gabriel area. And this is the ideal goal that we achieve. Say these 2 stations have similar behavior and these 3 have similar behavior. But remember, we are working on time series data at different scales. So for our production system, we do this grouping based on different temporal scales. We did hourly, daily, monthly, and year. So we did a very simple approach to identify the clusters. We just take the time series data and we ran a K-mean. We just ran a K-means cluster and we ran it with multiple Ks here, and trying to find the overall point to identify the best K for this data set at different temporal scales. And I think this is hourly result. So for the hourly result, we have 8 groups. Now we have these 8 groups. We know these 8 groups within group stations will have similar temporal behavior. Next step is we want to find out what are the built-up environment variables, or what are the specific geographic feature types, and from what distance will impact this result. So if you just look at this, based on our hypothesis, locations with similar built environment will have similar temporal patterns. So these 2 might have similar built environment, and these 3 will have similar built environment. But we just don't know what are the variables that can help us to describe the built environment. So we start from using every variable we can. This is what we did. For a monitoring station, we start to construct all these concentric buffers, and each buffer will intersect with the geographic data we collected from OpenStreetMap. For this example, this is linear features, which are lines. So monitoring station A has within 100 meters, has 30 meters of motorway, and has 10 plus 13, this is 23 meters of pedestrian road. So you look at here, you have pedestrian road, 100 meters, you have pedestrian road with 43 meters within 200. And we start to construct a lot of buffers, and each buffer or each component in that feature vector tells us 2 things: specific feature type and distance to the monitoring station. We did that for polygons as well. So polygons can help us understand area size for example, here we have park and industrial land. And in 100 buffer, we have 500 square meter park and 0 industrial land. We did that also for point features. Point features, we just count the number of feature types we have. And in this example, in 100 meters, we have 2 apartments, 0 factory. 200 meters, we have 8 apartments, 3 factories. So from this table, we can derive some type of feature vector here. And if you think about this, when we add more buffers, this one becomes longer and longer. So eventually, this is the feature vector that we use to describe the built environment. In our system, we create a buffer from 100 meters to 3,000 meters. So we have about 3,500 components in the feature vector to describe the location. If you look at this feature vector, here's some examples. It shows you pedestrian road 100 within 100 meters, you have 23 meters, and you have park within 100 meters, that's 500 square meters. Also have distance to ocean, factory within 200 meters, we have 3. So now with all these feature vectors, we call it geographic abstraction. We want to be able to take this and derive the clustering result. So why is this important? How does this help us? if we have these feature vectors to describe the environment, and we have the clustering results say this too has similar AQI, if this can predict this, that means some of the component here can help us identify similar temporal behavior. And this component in the feature vector will be important for predicting PM2.5 AQIs. So this is the approach. We take all these feature vectors, and for each feature vector, the predicted label from the clustering result is used in a supervised learning way. So we train a random forest model. Every feature vector will predict the class label. And the random forest model tells us the importance of each component in supporting this decision. Something like this. After the random forest model, we know that pedestrian road within 100 meters is not very important in supporting this clustering result. That means pedestrian road within 100 meters does not really have a high impact of PM2.5 AQI behavior over time. And we do this for every component, and we take the importance value, we weight it on the geographic abstract. So you can see that before, this is the raw data to describe the built environment. Right? Pedestrian road has 23 meters. After we run the random forest, we generate the weight. Now we know it's not very important, so now it's 0. We can even remove this component. Motorway, 100 meters, is somehow important, so we still have 3.27 here. Apartment within 200 meters, not very important, so it's 0.041, very low. Motorway. So we call this geo-context. So what is geo-context? Geo-context is an updated version of the geo-abstraction vector. But this geo-context tells us how each feature type within a certain distance will affect this temporal pattern. But remember, every component has two properties. One is feature type, the other one is distance. And this geographic context rewards important or relevant features and penalize the others. Now we have the geo-context feature. To predict the PM2.5 AQI for a location at a specific time, we first create the geo-context vector for every monitoring station at that specific time. So you have the feature vector describes the built environment, and it's already weighted by the importance of each component, and you have some measured AQI. At least you have 12 of them. For a new location, we train a regression model, and that regression model will take the new location's geo-context vector and predict an AQI number. So that's the entire approach. So now I want to show you some experiment. We only have 12 stations, so we don't really have much ground truth. Or we did we have two ways to verify the result. The first one is we take these 12 stations, we did the leave one out cross validation. We hide one station, we use the other 11 stations to predict the leave one, the left one's AQI value. And the second experiment is we just predict for lots of locations in Los Angeles and put it on a map to see if that makes sense or not. So for the second experiment, we generate a fishnet, which are lots of grid, are 1 mile apart, and they cover most of the Los Angeles area. For our first experiment, the leave one out result, we test our method with 3 different temporal scales, hourly, monthly, and daily. We also try to see if we can just use the raw data, the raw geospatial abstraction, the feature vector that describe the built area without any weight, to help us to make a prediction. So we tested geo-context, geo-abstraction, and IDW. IDW is a classic spatial interpolation method in GIS. IDW works like this. If you have a point here, you want to predict the point's value, and you have a bunch of observations nearby, the value of these points is in relationship to all these nearby points, but the closer the observation is, you will have higher impact to the unknown location. It's a very simple method. It's very fast, but the result is not very good. I'll show you in the next slide. But just if I leave one out, our result predict pretty good. Our approach predicted very good monthly and daily AQI prediction. These are our result, and these are Abstract, and these are IDW. But they're pretty similar. So, for example, RMSE for our result monthly is 2.5, IDW is 2.8. And these are somehow still within 10% error. When we are not doing better than IDW, that will be hourly. So hourly is lecture rate much more than monthly or daily, but still within 10% error. The 10% error is important because all this monitoring station has a 10% uncertainty. So if you are doing air quality prediction or forecasting and your results are within 10% error, you probably don't want to spend more time to improve it because you don't really know the ground truth is correct. The reference data already have 10% uncertainty. So some visualization of the result. On the x-axis is the time, y is the predicted AQI values. These are from different monitoring stations. So y-axis is the predicted errors. So the red one is IDW, green one is our geospatial context, blue one is the raw data describe the environment. You can see that we are very close to IDW, and many times our approach works better. But more interestingly would be this map. So if you look at this, the map on the right, it's the IDW result. Everywhere in Los Angeles looks similar, only downtown looks very different. But from our approach, we will be able to predict very fine scale variations of this PM2.5 distribution. Somehow, if you look at the map, you will be able to spot highway on our result, but you will not be able to do that for IDW. But remember, in our approach, we did not use any traffic information. We only take the nearby geographic feature. So we think this is pretty nice. And surprisingly, we identified areas like Glendale as really bad in many of our tests.
I mean, it's not surprising you'd see highways because highways are an input, right? That there's within 100 meters a highway.
Right, but we don't really know, for monitoring stations, we don't really know monitoring stations are near highways. Because for EPA sensors, for EPA stations, they usually monitor in the background.
But what you're doing is for every small area, you're using the geographic abstraction to say there's a highway nearby, so the air quality will be good or bad based on its affordance, right?
Yes, highway is one of the components. On the left side, you will see that's the component that we use for prediction. And something more interesting here are roads are important, and within 600 meters, 700 meters, and railroads are important, primary roads are important. So when we say important, we mean this feature at that distance has a high impact to air quality. But we don't really know if it is positive impact or negative based on our other things are land use type, universities, village, and wetland. We were guessing that universities attract a lot of traffic. So although we don't use traffic, this type of features can act as a surrogate traffic features. Yes.
So I think most of the air quality really correlated with the time, right? Is it like the air quality in the morning or air quality in the weekdays or weekends? The probably are different, and because there are not so many cars during the weekends.
Right.
And did you have any results on the time?
Yeah, so the here is the time. So this is the daily, hourly, and monthly result. So what we did for that time component is for every hour when we have some readings from the monitoring station, we retrain the model to compensate for the time variation.
But I mean, did you try adding the features in your experiment?
Yeah, we can add the time. We didn't add time.
You didn't.
We
Okay.
didn't add.
Thanks.
All right, so that's the experiment. Now I want to show you some related work. There are three main types of air quality prediction. People will use spatial interpolation, like I show you for the baseline approach, use IDW or kriging. But this approach only considers the spatial distribution. They don't really consider the neighboring characteristic of the built area. Dispersion model is also very commonly used, but this dispersion model is really complicated. You need to build 3D models of buildings. You need to simulate the airflows. Our approach is that we only use easily accessible data, and you can see the entire approach is not really complicated, and we can run it every hour, and for different regions, we need to retrain in the end. The last category is land use regression method, like I showed you in the table. For the land use regression method, it heavily relies on experts to select important features. You can see our approach is more automatic feature selection part. We will be able to tell you what are the important components and from what distance would affect air quality. So summary here, I show you a data mining approach to build an accurate model for predicting PM2.5 concentration, especially at fine spatial scale. And we can automatically select important features, and this will be also important result for people from the medical school. Let's say you want to study kids' asthma, you want to know small variations of air quality. So some of our ongoing work, we want to test our approach for different cities, cities in the US and other cities. We are also testing our approach for data from Beijing. And we want to incorporate other time series data like weather information. Weather information is, our current result shows that it can improve some of the prediction result, but we haven't really figured out how does it work to incorporate a dynamic data set that change over time and space with static data set that we are working on right now. Also for the other question about small devices to monitor air quality. This is Purple Air. So for Purple Air, or another site is called Airbeam, they have this pretty cheap device that you can install. It's $179, and it's very accurate based on our AQMD study. You can install the machine on your house, and it will pick up PM2.5 values and also other pollutant type. And this map is to show you these sensors in Los Angeles. You will be able to see that there are some variations, like here you have a 38, but the nearby one has a 15. So this might be a good way to verify our result, but this is not, this type of sensor could pick up sudden changes often. Like if a car drives by, you will have a really high PM2.5 at that moment. So people usually take this time series data, this recorded time series data, and do a 24-hour average to represent the result. But this is one type of source we want to use to validate our fine scale prediction. And finally, another work we are doing right now is we want to do forecasting. So prediction is for the same time for the locations that do not have sensor. How do we know the value? Forecasting is for the future. We are building this general approach to do location-dependent time series data forecasting. So AQI is time series data. It's location-dependent, if one location will be similar to the other location. Existing approach, if you are familiar with time series data, they don't really work well with spatial correlation. That means they usually work on one time series data, like a RIMA, a model regression model. These are great method if you only have one time series data, and they do very well in our experiment. They do very well in forecasting the next 6 hours air quality. But after 6 hours, it doesn't really work well. So our approach is we are building a deep learning model to do this forecasting. And what's interesting for this deep learning model is I want to show you. Here we have the air quality time series, and each of these time series has a location. So remember, if you only use the monitoring station, you have 12 time series data. After you have the time series data, you generate a graph to indicate the relationships between this time series data, and the convolutional layers will help you to generate the new representations of this graph and time series data, and then we use a recurrent neural network to help us to do the forecasting. But if we only use 12 locations, it's not very useful in the beginning, and there's not a lot of training data. So with our predicted values, now we have more time series data, and we can construct their relationship using this geo-context. So every time series data, every predicted time series data and the ground truth time series data will have some similarity based on their geospatial context. And we can use that, construct a graph, generate the raw data, and put it into the CNN and RNN to do forecasting. So we are working on this right now. These are all the people working on the project. Yi Jun was leading the project since last year, and other students, also Dimitris and Service, other people at Ecumenical School, Sandy and Prima. This is an NIH-sponsored project. Microsoft also helped us for the infrastructure, and I really want to thank Jose Luis because he paid for the project, but he's not here. If you're interested, we also built this website so that you can look at air quality in John Snow at USC.edu and show you the live demo.
It's John Snow.
Yes.
Who came in France?
Oh.
Our
The
GPU
Windows
server is
coming.
ARIA.
Yes.
ARIA never died. This is historical data. We are producing real-time data, but it's not on the map yet. We're still working on to make this look nicer. But if you zoom in, you'll be able to see binary prediction result. And if you click on any location, you'll be able to see a PM2.5 prediction. Like 58 is not okay. Above 50 is not okay. And you can go to the next hour. I'm sure this.
You can blame eyesight virus.
Can I ask a question while you're trying to demo? So it seems to me that you use this feature, which is the radius around the point. But in Los Angeles, right, the prevailing winds have a huge impact in terms of the pollution. Like, so, for example, most of the year, prevailing winds are actually coming off the ocean. So, like when you look at your estimates for Marina Del Rey, it seems like, well, they would be influenced heavily by sort of prevailing winds and sort of the geography of a given area.
Yeah.
Is there some way to compensate for that? It seems like you're not really taking that into account.
Right, but I think that's more important for forecasting for wind, because we are talking about. So right now we are talking about at a given time, what are the measurements? Right, so at a given time, if we have measurement of these 3 locations, and the build-up area, the build area is similar, what are the predictions for this area? And for future value, we will need to consider the weather information more carefully. Because right now, when we use weather information, it doesn't really help much in this prediction. I think it depends on different types of pollutant. PM2.5 should have a huge impact.
But let me give you an example, which is that I could imagine that you pick 2 areas, one that's in Pasadena, and it has, let's say all residential around it. And you pick another one that's right here by the coast, it's got all residential around it. So the features look almost identical. Yet because of sort of the geographic regions, right, as long as the prevailing winds are in general for that day are coming off the ocean, then in fact they probably would have radically different PM2.5 levels.
Right, I agree. So we have a component called distance to the ocean that could probably compensate for that.
Okay.
But still, we are looking for methods to incorporate these dynamic features with weather.
So I have a related question. Just to kind of try and put this together, because it's interesting because you don't really sound as if you have a theoretical kind of model that you're working from in terms of how you think the physics of the situation works. You're basically modeling the feature space and then running machine learning and using the tools that you can to look for correlations and to fill in the gaps and do that kind of stuff.
Right.
So just to kind of if one was to try and build a physical model or a kind of a theoretical approach of how you see this stuff working, it sounds as if you kind of think of air pollution as being generated locally and like by the land use and by cars and by all this kind of stuff, and then basically kind of dispersing pretty isotropically, thank you. And then basically that's the kind of prevailing underlying mechanism that you're seem to be working. And that correlates nicely with the type of features that you're defining in your space. So land use and all that, and roads and presence and location to the ocean and that kind of stuff. Right. That's really interesting as a general methodology. So in a way, good feature engineering sounds as if you're kind of replacing physical modeling with good feature engineering, and that actually does a good job. Would you comment on that? Is that strategically kind of how you thought about it?
Right. So building a physics model to describe the environment for modeling air quality. People have been working for that for many years, and it's continuous work. But that's very expensive. It requires building a very detailed model of the city and how the air flow. So that's one type of approach. The other type of approach would be more similar like this land use regression. They take lands and they try to find a correlation between lands and air quality. I think the strength of this type of data-driven approach is we will be able to select important features. So when people are building 3D models or building a dispersion model, they will know where to start and where to look at these features. So we don't see this as a way to tell people distance 200 meters from highway is important. I don't think that's our conclusion. Our conclusion or our finding is 200 meters to roads might be important. This is a hypothesis. Are we going to verify that with some ground truthing, with some local sensors or other methods? This way we can reduce the hypothesis space to a smaller one, so people in like air quality experts, they could have something to start to work with.
One question about the weather again. It's like, how do you model El Nino? So when Craig's talking about the typical normal situation where the wind's coming off the sea, right? But sometimes you get an inversion effect and the air blows in the other direction. And on those days, if you look out the window, you see this thin line of brown stuff over the sea.
Yeah.
one would predict, therefore, that on those days, the air quality may be completely different on the city because of the direction of the airflow. And yet, because you're basically kind of assuming that distance from the ocean is always relevant, you won't I mean, my assertion would be you wouldn't necessarily capture that effect.
Right.
It's relevant, it's just inverted.
Right.
Yeah, but so would the system be able to take that into account? Probably not, because you don't know which direction the air is flowing.
The direction to ocean tells you, well, the distance to ocean tells you, I think it will compensate for the direction, but I'm not exactly sure.
Because it's completely directionally opposite.
Right, but if your observation tells you when you are far away from ocean, you have good air quality, then the model will pick that up.
But so my point is, on rare days when there's an El Nino, which over time the data will be the predominant data will be telling you this isn't the case, but in the small number of situations where the air is flowing in a different direction, your model won't pick it up. So maybe that could be something you could look for.
Yeah.
And
because the second, so we have two models. We have two machine learning models. The first one is the static one. The second one handles the time variance one. So for that case, we need to be able for the second model to pick up that change over time. But it's an interesting problem how to incorporate weather information and all this dynamic information with others.
So, in my opinion, population density is a very important feature. So why not add population density in this model?
So I like all your guys' question about adding more features to this model. It's feasible. We can just add lots of features. It's just we don't really think about all these variables into these models. But if you think about this, we didn't add traffic, but some of the data tell us about traffic, like hospitals, the traffic. And population is important, but density of buildings is actually captured in that feature vector. Right? It tells you within 100 meters what are the buildings within this 100 meters. This somehow tells you if it is 100 meters and you have lots of office buildings, tells you this is a work area. Only during certain day you have people. If this is residential housing, it tells you that a lot of people live here. So somehow population is there. Right?
Another question is that you mentioned you use the random forest models, but why do you pick that models? I'm just curious.
That's a very good question. Because we use Spark MLlib. It's very convenient. So there's no good explanation for that. And one good thing is it tells us the weight of each component.
So very interesting thought. Thank you. When you have the RMSEs on that table that you compared the results, so if I remember correctly, the RMSE was around 5. So the range of values you're predicting is out of 100.
It's smaller than 100.
Oh, so it's around 2. And so you're predicting the range of values you're predicting is out of 100.
Los Angeles, I think, is 30 to 60. That's the range of the value.
No, so you're getting that error out of 100 or out of 30?
The range. So this RMSE is taking.
Is it normalized or 100? So
it's not normalized.
So that depends on the value you're predicting, right? So the value is between 0 and 100, right? And you're getting 2% error basically. Is that true?
Yeah, but the value, the ground truth value is not from 0 to 100. It's about 30 to 70.
Okay.
So when you talked about considering industries, do you consider the type of the industry in the feature? I mean, I know again it's a feature question, but I feel like when you say distance to, so if there's an industry between this distance, I think it's important to consider the type of the industry because.
Yeah, it's in the type of industry should be in the point data. It tells you what type of building that is. For land use data, it only tells you this is industrial.
So I'm surprised the IDW does fairly well compared to your approach, right? Is that the right? And so that's sort of surprising, isn't it? That it does so well, given that there's far more depth to the features you're using. So why does IDW do so well? What if you just compared against predicting the average, like 60 for every station for every year?
I think IDW works very well in most of the spatial interpolation cases. If you carefully choose the P, there's a P that you can choose how you want to invert the distance. We did fine tune that IDW to make it work well, to just compare our approach to a good baseline. But the problem of IDW is actually not just the prediction for this 12 station. The problem of IDW is the service is very smooth. So it's like this.
Right. Yeah, I remember that. But it might be a better prediction, even if it's smooth surface, right? So do you have something?
We don't know that.
Right. Yeah. So I mean, but you were looking at that personal station, right? Do you see the same sorts of trends that you're showing here when you look at that website? Do you see, for example, people near the highway have a much higher AQI than the people who are further away?
Yeah, and for some locations as well. But we don't, I don't want to, just from very initial look at the data, but I don't think I can come up with a good explanation now. Because all this monitoring station, we still need to be careful about like the sudden change. Do we want to incorporate the sudden change? The sudden change might be important, might not. And also for it's cross-sourcing air quality data has been around for a while, but still people are cautious because you don't really know the quality of the data. You know the quality of the machine, but you don't know how people install it. Install the machine is important.
Right. I mean, it's just unfortunate because I feel like the metric you're using to evaluate doesn't really highlight any strength of your method, and it seems like there's probably a strength that you're missing in those results.
Right. I think evaluating the fine scale would be a good way.
Okay, so let's end it here. Thank the speaker once again.